Okay, let's start. Hi everyone, and a warm welcome to this exciting series on quantum technology. I'm Asfal Tafsha, a PhD student at Department of Electronic System Engineering at IISc Bangalore. I'll be your host today, and the series will be co-hosted by Uday. Uday, you may want to introduce yourself.
Yeah, thank you, Asif. Hello, everyone. Welcome to the Q series. I'm Uday. Currently I'm working as an engineer at MathWorks. I work on MATLAB and Simulink. And apart from that, I graduated from MTech in quantum technology from IISc, and I'm in the pioneering batch of this program. I'm passionate about bridging the gap between cutting-edge quantum research and practical applications. Looking forward to have a great session today and tomorrow. Thank you for joining.
Thank you, Uday. So before we start our series, I would like to give a brief overview of quantum technology. Quantum technology is an emerging field that leverages the principle of quantum mechanics, the fundamental theory that explains the behavior of particles at the smallest scales. Unlike classical physics, which governs our everyday world, quantum mechanics introduces fascinating concepts such as superposition, entanglement, quantum tunneling, which open up revolutionary possibilities. Quantum technology is no longer just a subject of theoretical discussions. It's rapidly shaping the future of computing, communication, and information security technologies. These technologies are rapidly advancing, and major companies, governments, and researchers from across the world are heavily investing to bring them into practical use. The future is incredibly exciting. Whether you are here to explore the fundamentals or stay updated on the latest advancements, the series is designed to inform, inspire, and ignite curiosity. We have an incredible lineup of speakers and experts from both academia and as well as from industry who will share their knowledge and experiences. So I encourage you to make the most of it and engage. If you have any questions, you may drop them in the chat box. Now, starting forward, we would like to invite Lila. So Lila Cadi Tazi is a PhD student at the University of Cambridge, working in Alex Thom's research group. She's a quantum chemist specializing in quantum computing methods for electronic structure analysis and the development of resource-efficient algorithms for near-term quantum devices. Her research focuses on error mitigation techniques and their integration into quantum computational workflows. Recently, she embarked on an interdisciplinary project combining machine learning and quantum computing to address complex problems in chemistry. Lila completed her UG and master's training in France at ENS Paris-Saclay, where she built a strong foundation in theoretical and computational chemistry. She subsequently earned an MPhil in chemistry at the University of Cambridge before beginning her journey in 2023. And with this, we would like to invite Lila for her talk on quantum algorithm for chemistry simulation using machine learning. Lila, you may please share.
Thank you. Okay. Can you see my slides?
Yeah.
Okay, so hi everyone. Thank you very much for the invitation. It's a great pleasure to talk here today. So I will present my recent work on an algorithm called QUACE, which stands for Quantum Atomic Cluster Expansion. And our very general goal is solving chemistry problems with machine learning and quantum algorithms. So this is joint work with my supervisor, Alex Thom, and two other collaborators, Gabor Chani and his student, Ilyas Batatia. Okay. So the very general problem that we're trying to solve here is that of theoretical chemistry. So very generally, if we have a molecule, we want to predict its energy, maybe the forces between the atoms and other properties of this molecule. There are many quantum chemistry algorithms that already exist, such as Hartree-Fock, DFT, but they become inaccurate and very costly for large systems. So you can see in this graph that the more atoms you're trying to compute, the more atoms you're trying to simulate, the less accuracy you can get because of computational cost. So, okay, let me put, yes. And recently there has been the development of machine learning force fields, which are basically trained on DFT data, for instance, and can reproduce the accuracy of DFT data for a fraction of the cost. So these are very interesting methods, and this is how they are trained. So basically you have a machine learning model. In this work, we're using one that is called MACE, and you train it on some DFT data, so very computationally inefficient and costly algorithm, but which gives very good answer, very accurate answer. So you're able to train your machine learning model on that, and then later with new molecules, new structures, you can predict the energy and the forces for a fraction of the cost. So basically the prediction after the training will be extremely fast. So this MACE model, this MACE machine learning model, has been tested on numerous different systems and has been proven to be very efficient and very accurate for a very large number of different systems. So this is why we are really focusing on that, because for chemistry and computational chemists, this has a very large interest. So the idea of this work is to take the MACE algorithm and make it quantum. So the workflow would be the same, except that inside of the MACE algorithm, there is one step which is made on a quantum computer. And in particular, it turns out to be a tensor contraction, which we make on the quantum computer. But the rest of the workflow is exactly the same. So this is what I will present today. So I will briefly introduce MACE, this machine learning algorithm. Then I will present my work, which is the quantum reformulation of the problem, and the QUACE algorithm, which is the quantum version of it. And then I will present very briefly some scaling results and applications. Okay, so the MACE algorithm works this well because it embeds some very fundamental symmetries into the machine learning framework. So in particular, we know that if we translate our molecule, the energy should not change. And in the same way, if we rotate the molecule, likewise, the energy should stay the same. And also, if we permute atoms of the same type, the energy shouldn't change, right? So the point of ACE and MACE is to embed those symmetry directly into the machine learning model, so that they are always present. We're sure, like by design, they are inside. Oops. Okay. So the way we do this is by building basis, a numerical basis that has those symmetries. So we start with our molecule and we regard this as a graph. So we have one node for each atom and one edge for each bond in our molecule. Then we will build what we call the one particle basis. So this is done by simply putting radial and angular expansion onto every edge of the graph. So every bond, okay? So this is what we create edge features. So every edge of our graph has some feature which are these one particle basis. What comes next is creating many body terms. So first we actually sum the one particle basis, so the edge basis, we will sum it over the neighborhood of each node. So this means that we are creating a new basis now that is called this A basis. And this has basically the information of what is around node I, okay? So in here, the indices are just the angular momentum and quantum numbers indices, and Z is the atomic number of atom I. So now we have these information about the neighborhood of each node, but it only has two body terms because we have only summed those edge features, which are for each node. So sorry, for each edges. So only two body terms. We know that chemistry and like physics is not only two body. So we want to create many body terms. We do this by taking a tensor product of those A vectors. So my atomic basis vectors A, I will just take tensor product of them up to a certain order nu, okay? And this creates what I call the product basis, which is like this bold A basis. And in there, we will have nu plus one body terms inside of this new basis. And this new parameter I call the correlation order. And this is just a hyperparameter that I can take lower or larger, depending on how many body I want to create, okay? So what comes next is the symmetrization. So because I said we want to have this rotational symmetry in the network, we're going to symmetrize our bold A basis by averaging it over all the rotations of the sphere, basically. So in practice, this is done by summing with the Clebsch-Gordon coefficient. So here we have just a tensor product between my A basis and the Clebsch-Gordon coefficients for the sphere. And then this is a tensor contraction, okay? And we end up with this symmetrized basis, which now has permutation and rotation invariance. So our symmetries are enforced inside this B basis and this symmetrized basis here. And we're going to use that basis to build an expansion of the energy, for instance. So this is what is called linear ACE. It is just taking a linear expansion of those B vectors and to represent the energy. Or you can also use that B basis in a more sophisticated way. This is what is done in MACE, where the B vectors are used in a message passing architecture. But the idea is the same, is like now we have those very, basically those are like, this is a basis to represent the molecule, but it has symmetries inside it, so we can use it in a machine learning architecture. Okay, so now this is just a technicality, basically in the MACE embedding. Both indices Z and N are embedding into a single channel, so this is why there are going to be K indices from now. Okay, so MACE is actually a very successful algorithm. It was able to represent a lot of different chemical systems, but it still has some limitations, and in particular computational limitations. So basically, we are restricted in the angular resolution of the models of the networks. So this parameter here, Lmax, is like the maximum angular momentum in the radial, in the angular expansion. And if we make it exceed 3, it actually becomes too computationally inefficient and it cannot fit into GPUs, basically. And in the same way, we are limited in that correlation order, so that how many body terms I'm going to have in my model. We are also very much limited computationally. So this means that even though we can simulate a lot of things with MACE, we are limited in the design space that we can explore. And actually, in terms of speed, even like small MACE models, they are not fast enough for some applications, like biological system applications. So looking for a speed up of MACE would also be beneficial for some applications. It turns out that the bottleneck operation is that tensor contraction between my A vectors and the Clebsch-Gordon tensor. So let's look at it into details. So how it goes is I have those one particle basis vectors. I do a tensor product with them to get my product basis. And then I do this tensor contraction here to have this B basis here. And actually, you can see that I start from a very small vector and I end up to a very small vector. But what is in between is this very big computational space, which is a tensor product basis, where I do this tensor contraction, which actually is a very highly dimensional object. So this is where the computation is going. This is the inefficient step of MACE. So the point of this project is answering a question: can we actually do this on a quantum computer? It seems like it's well suited because we have like a few data in and a few data out, and in the middle we have that very large computational basis. Plus the operation we're making is a tensor product, which happens to be pretty natural in quantum computing. So this is the idea: getting those vectors and those vectors inside a quantum circuit, making the right operation, so the tensor product and contraction, and getting those B numbers out. And this would be just a better scaling of the MACE algorithm. Okay, let's get to it. So as I said before, the overall workflow is the same, but there is just now this tensor contraction that goes into play, and now you can understand what this operation is specifically. So if we wanted to reformulate the problem in terms of qubits, we would see that first, to represent this vector, which has this size in terms of like hyperparameter of the model, so Lmax plus 1 squared, we only need a logarithmic number of qubits, okay? So the number of qubits we're going to need is that one, which is the logarithm of this. And now what we need to do is first loading those A vectors onto our qubits. So with that NA number of qubits here, represent them as a quantum state. Then we need to make sure to make this tensor product. Okay, so we're going to do this tensor product of those A vectors that we've just loaded. Then we also need to load the Clebsch-Gordan coefficient into a quantum state. And then we need to do that tensor contractions, which actually happen to be only a dot product, okay? So we need to make the dot product between the two states, the two quantum states that we've just created. Okay, so how do we do the encoding? It's actually pretty simple. We're taking our classical data in a vectorized form, and we are encoding each of the vectors' coefficients into the amplitude of a quantum state. Okay, so this is where the logarithmic number of qubits comes. So I will just, every amplitude of my quantum state in my 2 to the power of n basis is going to be one coefficient of my vector. So there are algorithms that exist to do exactly that. One is called the quantum Shannon decomposition. This is the one that we're using in this work. And basically, it just means that I can now load my A vectors and my Clebsch-Gordan coefficient by using a gate that I have pre-computed classically, basically. And it will create this state. Okay, so now how do we do the tensor product? In quantum computing, the tensor product is actually very natural. You don't have anything to do, basically. So the point is that if I create 3 times the same state, UA, using that gate that I have just created, and then I consider the state of all of the qubits after those preparations, it will turn out to be the tensor product of 3 times the same vector A. And that is just because several quantum systems taken together, their overall state is the tensor product of each individual state, right? So it turns out that we don't have anything to do to make the tensor product. We just need to prepare those into like parallel quantum registers. And the tensor product is just done by quantum, basically. So this is pretty neat. So now we are able to load the Cleptron, load the A vectors with the tensor product is like done. We need to work out how to make the dot product now. Okay, so how do we compute that dot product? You will maybe know an algorithm called the swap test, which looks like this. So if you have a state A and a state C, and you just add one ancilla qubit, you do this sort of Hadamard test with a control swapped gate, and you measure only the ancilla qubit, you will be able to get this information out. But as you can see, it's actually the squared modulus of the tensor of the dot product, sorry. So this is not really what we want, because basically we lose all the phase information in that measurement. So we don't have all the information we need. So we could turn to another algorithm, which is called the Hadamard test. And in that one specifically, we're going to use that gate here. And this works, so we can get the dot product out of this algorithm. But the problem is that it requires to do a controlled version of our preparation unitaries. And this is actually very costly. This would be too many gates. So we wanted to come up with a new framework that would do this operation with not that many gates, basically. So this is the one that we're using. It's called the one control test. This is a new circuit design that we have made especially for this project, where basically you can see we sort of combine both algorithms here, and we only have one unitary that is controlled and the other isn't. And then we still do have these control swapped gates, and we can measure now the right quantity with the phase information. So you will say, okay, there is still this controlled unitary, but remember this unitary here was actually this one. So it is a separable state unitary, basically. So the number of gates in here it can be decomposed into controlled gates very easily. It's not as bad as the UC gate, basically. And this is just a little comparison of those approaches. So you will see that basically we have reduced the depth of the circuits by a lot. And the number of like 2-qubit gates is also very much reduced. So we have a pretty good quantum resource reduction with that algorithm. This again is a comparison of both algorithms. You will see that the Hadamard test resource is growing like that, and we have a much favorable scaling with the one control test. Okay, so this is the full QUACE algorithm now. So we start with our A vectors and our C tensor. We turn them into quantum gates, UA and UC, and we plug them into this one control swap framework. So, and then we just have one qubit to measure. It is that ancilla qubit that we have added to our circuit. So this is just one qubit measurement. And there you go. You have measured your symmetrized tensor and a vector, sorry, and you can go ahead with MACE. Okay. So why is this better than the classical MACE? In the classical MACE, the circuit, the scaling, sorry, is like this. So you see we have an exponential scaling with the new coefficient. And in the QUACE algorithm, so the quantum one, we actually end up with a logarithmic scaling in L. And in L, sorry, and also linear scaling in U, whereas here it was exponential. So we do end up with a better scaling, an improved scaling of the quantum algorithm. Plus we measure only one qubit. And then in terms of circuit depth, so the implementation that we have now has this scaling in terms of 2-qubit gates, but this is using the quantum Shannon decomposition, and this could definitely be improved in the future, so we could reduce that depth scaling by a lot. So what are the applications? So so far we are running 1,000 shots application with simulators of quantum computing, of quantum computers, and we can do what we call molecular dynamics. So basically we can study the molecules dynamically, which can be very useful for yeah, I mean it would be very useful for chemists in the future, hopefully. Okay, so that is about the end. So what we propose in this new framework is a more compact way of doing chemistry compared to what other algorithms exist, like VQE or algorithm for quantum chemistry using quantum computing, because basically we have no scaling with the system size of our quantum circuits, so either depth or number of qubits, because we just do several quantum circuits in parallel, basically. So this also allows us to study larger molecules, which is which is like a good improvement for quantum chemists using that technology. The QUACE algorithm, if it ever runs on large hardware, will also make a better design space available for MACE, basically, because of those limitations in the classical MACE that we could maybe improve with quantum hardware. And in the future, yeah, we want to have a better implementation of the preparation gates. And we also want to stress out that our one control test method for the dot product, it can be used in other contexts. And actually this is now published. So if you ever want to compute a dot product with a quantum circuit, I recommend you go and see what we propose here. We also have another circuit that has absolutely zero control on the unitary, so that can be useful in other contexts too. I want to thank my collaborators, so Gabor Chani, Alex Tom, and Ilyas Batatia, and as well as my research group, funders, Continuum, and thank you very much for your attention.
Thank you. Thanks a lot, Lila, for this interesting talk. We would like to see if you have some questions. It looks like we have no questions. Thank you.
Thank you.
Thank you once again.